All right, let me just get my other device hooked up here. That's my name. Okay, perfect timing. Let's see. Start by noting that there's no class on Wednesday. Wednesday is Veterans Day. But Wednesday night, that was the most popular time for a review session. So we'll have a midterm review session Wednesday night at 8. On Friday, we'll have the midterm, whether you're in the regular grading option or the alternative grading option, you will find a midterm posted on Blackboard at 10 a.m. You have until 2 p.m. to submit it. And I have another meeting during that time slot, but I will have my email open the entire time during that time slot. So I won't be logged into the Zoom meeting for this class, but I will be able to reply to email immediately because in most of the meeting is sufficiently low stakes that I can say, sorry guys, I gotta take an email. Any questions on anything?
Yeah, for the alternative grading, what should we be expecting on the test or on the midterm?
It'll be stuff from alternative problem sets 10 and 11.
Okay, thank you.
And for everyone else, will be stuff from problem sets 9, 10, and 11. Anything else? Okay, last time we reviewed differential equations. The most important thing to remember about linear differential equations is that any linear second order ordinary differential equation has two linearly independent solutions and requires two initial conditions. Those are facts that we're going to need in what we're about to do next. Today, I'm going to talk about series solutions to differential equations, writing the solution to an ODE as a series. So we're going to assume that f of z is equal to the sum from n equals 0 to infinity of an z to the n. So we're going to basically be writing these solutions as Taylor series. And most functions, well, any continuous and differentiable function has a Taylor series representation over some kind of interval. So it's a valid starting point. It's a very general way to write a function. It's a very general way to write functions that either we simply can't guess immediately, like we'll do one where the solution turns out to be sine of square root of x, something where if we really thought about it, we could write out the Taylor series, or something if we really thought of it, we could say, yeah, okay, that's a valid solution to this equation, but it wouldn't be obvious. This is a first principles way to get at that. And sometimes the solution is some function that we don't already know. It's not some function on that list of things that you learned in algebra, polynomials, ratios of polynomials, square roots of polynomials, sines, cosines, tangents, exponentials, logarithms. There are more things in heaven and earth than are contained in your list of functions from high school algebra, Horatio, to paraphrase a quote from Hamlet. For those of you who don't know, I'm talking about Hamlet said when he saw his father's ghost, something supernatural, something that would be beyond ordinary experience. There are more things in heaven and earth than are contained in your philosophy, Horatio. Well, there are more things in math and physics that are contained in a high school algebra textbook. So we will get at some functions that simply aren't on the usual list. We're going to be studying differential equations of this form: d squared f dz squared plus p of z df dz plus q of z f equals 0. And people, whenever I start writing down equations, immediately ask for the application. This will show up when we solve the wave equation in different coordinate systems. And a lot of this will also show up next year in quantum when you're solving the Schrodinger equation. I will get to some specific examples of these types of equations in the next couple weeks. But this is one of those things where first we just really need to get technique down before we get to specific application. Otherwise, I just say, because there's often a few steps going from the way that the wave equation is normally written to a differential equation like this, and involves some changes of variables. So we're just going to do technique for now. Now, in general, a lot of the times the equations are actually written in a different form. They're written as a of z d squared f dz squared plus b of z df dz plus c of z f equals 0. But what I'm doing is I am dividing everything by a of z. And we're doing that for two reasons. One is, of course, now we just have two functions to deal with, two coefficient functions, if you will, instead of three. And also, it turns out that this kind of equation is easy to solve when a is non-zero, because that second derivative matters. And there are important qualitative differences between a second order equation and a first order equation, just as there are important qualitative differences between a third order equation and a second order equation, or a fourth order equation and a third order equation. So whether a is 0 or non-zero matters a lot. And we can put all of this together by classifying two different types of cases. Is P of Z singular or non-singular? And is Q of Z singular or non-singular? It turns out that at a point,
Professor, what do you mean by singular?
a singular, does it have a singularity? Does it blow up?
Okay.
So if it doesn't blow up, if P and Q do not blow up, then they and F can be written as Taylor series or power series. So we can say that f of z is equal to the sum from n equals 0 to infinity of an z minus z naught to the n. P of z is equal to the sum of p sub n z minus z naught to the n, and q of z is the sum from n equals 0 to infinity of q sub n times z minus z naught to the n. All right, so if everything is nicely behaved, then we can, meaning nothing's blowing up, then we can write them as power series, maybe only over a finite interval. Possibly only over a finite interval. right? They might have a finite radius of convergence. There's no guarantee that we can write this out as a power series that's applicable from z equals minus 50 trillion all the way to z equals plus 50 trillion and beyond. But it is possible to write that out. That's a theorem. So let me give you some types of equations that, let me just check something. Okay, let me give you a few examples of equations that we can classify as singular or non-singular. One, the Hermite equation, which will show up next year in quantum mechanics. The Schrodinger equation reduces to this. It might not look like it, but it reduces to this in the case of a harmonic oscillator if you factor certain things out. That's written as d squared psi dx squared minus 2x d psi dx plus 2 times nu times psi, where nu is a constant, equals 0. This is important for the harmonic oscillator.
Another question. Your second differential, is that with respect, not with respect to, but is that a second differential of psi?
D psi dx, yeah.
Got it.
Yeah. If my handwriting gets any worse, they're gonna give me hospital privileges. Now, another equation that's really important is the Bessel equation. And this one we'll spend a lot of time on in a couple weeks. We already mentioned it before. It shows up when you take the Fourier transform of a circular equation, of a circular aperture. Z squared d squared f by dz squared plus z df dz plus z squared minus m squared f equals 0. Now, one thing to notice about this equation is that if it weren't for this z squared here, this would be exactly like the Euler equation that we dealt with last Wednesday, okay? There's only one term that differs, and it's an important term, but it's close enough to that I want you to think back. When we solved the Euler equation, we guessed that the solutions to the Euler equation would be a power law. And sure enough, they were. A power law worked for that. Well, when we solve the Bessel equation, we are going to make a guess that it is a power law multiplied by an analytic, by a power series, and I'll explain that in a little bit. There are a lot of things that happen when we do power series that are quite analogous to what happens when we solve the Euler equation, which is why I spent some time on it last week. And it's why problem set 12, which will be posted in the middle of the afternoon today, has a problem that goes into what happens when the Euler equation has degenerate solutions, because it's similar to what happens when the Bessel equation has degenerate solutions. Now, this equation doesn't look like this form, but if I divide everything by z squared, I get d squared f by dz squared plus 1 over z df dz plus 1 minus m squared over z squared f equals 0. And this is singular. But the good news is that the singularity is relatively well behaved. And what I mean, the question was, is the problem set due Wednesday? No, it's due the following Wednesday. It's due on the 18th. Okay, what I mean by it's singular, but it's a regular singularity, which is a special term that essentially means that although P of Z blows up but z times p of z doesn't. Q of z blows up, but z squared times q of z doesn't. And that's important. It turns out mathematicians have proved that even if p and q blow up, if z times p and z squared times q don't blow up, then we can still work with it. It turns out that there are easy ways to do this. If they do blow up, it's much harder. The good news is that most of the equations that we encounter in most of the physics you're going to see as an undergrad don't blow up. Don't blow up in weirder ways. If they blow up in weirder ways, those are very specialized topics, which honestly I have never had to deal with in my career. There are specialists who have to deal with them. You can go and ask one of those specialists how you treat those equations. One way to think about it is that if z times p of z is analytic, which means it doesn't blow up, it's differentiable, and you can write in terms of a Taylor series, and z squared q of z is analytic, then p could be written as some other function s of z over z, q equals t of z over z squared. And technically I should be writing z minus z naught, but we're dealing with a singularity at z equals 0. If the singularity was at, I don't know, z equals 5, then you'd replace z with z minus 5 everywhere. And if it was at z equals 1/2 ax squared plus bx plus c, then you'd replace it with z minus ax squared plus bx plus c, and so forth. So then we could rewrite our equation as d squared f by dz squared plus s of z over z df dz plus t of z over z squared f equals 0. And you're probably thinking, well, at this point, all he's done is do a bunch of renaming. He probably just wants to quote Shakespeare again. Well, no, actually, today I'm busy quoting Hamlet, not Romeo and Juliet. And by the way, speaking of Hamlet, you may have heard that they're killing a bunch of mink at mink farms in Denmark because of COVID. Something is rotten in the state of Denmark. Sorry, I love Hamlet. Okay, so the reason why I'm doing this is not just to engage in a bunch of renaming, it's look at the denominators carefully. Up top, we've got f, which is analytic, s times f, which actually f may not be analytic, but up top, we've got functions that we're going to write in terms of series. And then on the bottom, we've got something with units of z squared on the bottom. You know, your freshman lab professors always yelled at you to check your units. Well, checking your units matters. It turns out that a surprising amount of things in the more advanced realms of theoretical physics can be done by checking your units. And we've just written this as an equation where everything has the same unit, well, has denominators with units of length squared if z is a length, right? And that turns out to be important. That turns out to be why it is that we're able to do this. It turns out that that is part of why these equations behave so nicely. So here's what you should take away so far. Some of the equations that we're going to be dealing with, the coefficients don't blow up, except that, okay, I guess technically this coefficient blows up at infinity, but we're not worried about that. Some of them, the coefficients of df, dz, or f do blow up, but they blow up in such a way that we could write them as the ratio of an analytic function, something that doesn't blow up and is nicely behaved and smooth and differentiable, to z or z squared, and we get the same units in all of the denominators. And checking your units is important. Any questions at this point? So what would S be in this case? S of z over z would be 1 over z. So S of z is just 1. That's pretty easy. On the other hand, T of z over z squared would be equal to 1 minus m squared over z squared. So T of z would be z squared minus m squared. Hang on to that. That's going to matter. You don't have to memorize it for the Bessel function. T is z squared minus m squared. But you would just hang on to the idea that if the coefficient is s over z, then s is z times the coefficient. And if the coefficient is t over z squared, t is z squared times the coefficient. Hang on to that. One more example. R d squared psi by dr squared plus, we write it as m plus 1 minus r d psi dr plus nu minus m times psi equals 0. This is called the associated Laguerre equation. This equation matters because it shows up in the hydrogen atom. You're going to spend some time using that equation in quantum mechanics next year. Oops. And again, we can divide out R, and we'll see that there is a singularity, but it's a pretty nicely behaved singularity. We get d squared psi by dr squared plus m plus 1 minus r over r d psi dr plus nu minus m over r psi equals 0. And I'm going to multiply top and bottom by r just to make it manifestly obvious what the s and t are. You know, even if you get an equation where you look at it like, but I don't see something divided by r squared, it may not have been written explicitly with a big sign saying, hey, this is something over r squared, but it's equivalent to something over r squared. Any questions on this taxonomy of differential equations?
A couple. So what you have in red, you were saying that we can rewrite the numerator as a series. Are we going to touch on that?
We will, yeah. Be patient, a couple minutes.
Okay. And then the next question is right below same units. When you argue that s of z over z is equal to 1, how did you know that?
S of z over z is 1 over z because there was a 1 over z right here.
Oh, okay.
Multiplies the first derivative is s over z. Anything else? Anyone? Anyone besides Sebastian? Because he always gets the questions. Okay, let's start with an equation that we already know how to solve. I'm going to claim that we can solve this with a with a series. Let's say we've got d squared x by dt squared plus omega squared x equals 0. Now we know from prior experience that x has got to be c1e to the I omega t plus c2e to the minus I omega t, or equivalently, people usually write this as a cosine omega t plus b sine omega t. We know this from prior experience. And we're going to try this technique that I want to show you on something where we already know the answer from prior experience, for the same reason that you first test an instrument in the lab on some sort of sample that you already know the properties of. So let's guess that x is the sum from n equals 0 to infinity of a sub n t to the n. And we're going to engage in some Taylor series gymnastics here. dx dt has got to be the sum from n equals 0 to infinity of a sub n times n t to the n minus 1, because we just take the first derivative of each term. And likewise, d squared x dt squared is the sum of a sub n times n minus 1 t to the n minus 2. So far, I'm not telling you anything you don't already know, but I'm going to write this as the sum from n equals 2 to infinity. And the reason I'm going to do that is because, well, the n equals 0 term is 0, so we don't even need to include it. I can always leave out the 0, right? I don't have to write something, I don't have to write 5 equals 0 plus 5. It's just taken as a true statement. So I can leave out the 0. Likewise, the n equals 1 term is 0 because we've got this here, which is going to make the n equals 1 term go away. We've got this here, which is going to make the n equals 0 term go away. So if I decided to leave those out because they're 0 anyway, that would be perfectly fine. Then I'm going to say, all right, n minus 2. I don't like having different things. I could write this if I wanted to as the sum from n equals 0 to infinity of a n t to the n plus the sum from n equals 2 to infinity of a n n times n minus 1 t to the n minus 2 times omega squared equals 0. That would be my differential equation. Oh wait, no, the omega squared would go down there, sorry. My bad. That would be my differential equation. That's what happens when you write the terms in reverse order. I could write it that way. But aside from the fact that this starts at 0 and this starts at 2, this has t to the n minus 2 and this has t to the n. So I want to say that n minus 2 equals m. Then n equals m plus 2. N minus 1 equals m plus 1. A sub n is equal to a sub m plus 2. T to the n minus 2 equals t to the m. And if n equals 2, m equals 0. And when I make all of those substitutions, now I can write this whole thing as omega squared sum from n equals 0 to infinity of a sub n t to the n, because I'm not making any changes to the first series, plus the sum from m equals 0 to infinity, a sub m plus 2 times m plus 1, m plus 2, t to the m, all of that is equal to 0. Any questions on how I wrote that? Question was, should I shift n for the first derivative? By that, do you mean, should I start the first derivative sum from n equals 1? I could. I just didn't want to do the shifts until I had everything into its final form. But yes, you could shift the first derivative. Any other questions? All right, now I'm going to invoke Romeo and Juliet. Now I'm going to play that which we call a rose would by any other name still smell as sweet, and that which we call M would by any other name still be a valid index, okay? These two expressions are the same. It's just in one of them, I'm calling the first term M equals 0, and in the other one, I'm calling the first term N equals 0. But they're the same thing. So I'm going to rewrite all of this as just the sum from n equals 0 to infinity of t to the n times omega squared a sub n plus m plus 1, m plus 2, a sub n plus 2. And this whole thing has to add to 0 for any value of t, whether t equals 0 or t equals 1 or t equals 42 or t equals 14,605,000, whatever. It has to add up to 0 for any imaginable value of t, which only works if all of this is equal to 0. So omega squared an, oops, this should have been an n, my bad. All right. So an plus 2, if I solve this, an plus 2 equals minus omega squared an over n plus 1, n plus 2. You're thinking, well, how does this help us solve the equation? Well, if we know a0, we get a2. Then we get a4 from a2, and we get a6 from a4, etc. Likewise, if we know a1, we get a3, and we get a5 from a3, a7 from a5, etc. So if we have two numbers, a0 and a1, we get all of the coefficients. A0 gives us all even coefficients. A1 gives us all odd coefficients. Does that remind you of anything from the more traditional ways of solving this kind of equation?
Yeah, even and odd functions.
Yeah, we can break it up into an even and odd function. And furthermore, we know that, hey, one way of writing a solution is in terms of sines and cosines. So that should look familiar. Furthermore, the solutions are alternating sign. If A0 is positive, A2 will be negative because A2 is going to be -1 times a bunch of stuff times A0. A2 is negative, which means A4 is going to be positive because A4 is going to be -1 times a bunch of stuff times A4. And likewise, if A1 is positive, A3 is going to be negative. And if A3 is negative, A5 is going to be positive. So it's alternating sign. So let's say A0 equals 1. Then A2 is negative omega squared over, let's see here, n is 0, n plus 2 is 2, and n plus 1 is 1. A4 will be minus omega squared over 3 times 4 times minus omega squared over 1 times 2. Okay, that's going to be omega to the 4th over 4 factorial. And A6, well, I'm going to multiply again. A4 times minus omega squared over 5 times 6 equals minus omega to the 6th over 6 factorial. Huh. So looks to me like the even solution is going to be 1 minus omega squared over 2t squared plus omega to the 4th over, and I could write that as 2 factorial since 2 factorial is 2. Etc. What does that look like? What does that look like the Taylor series of from the functions that we learned Taylor series of a month or so?
Cosine function.
Cosine function. And then we could say A1 is 1. Well, A3 will be minus omega squared. Actually, let's say A1 equals omega because omega t will be dimensionless, right? And omega has units of 1 over time. So omega t will have units of time multiplied by 1 over time, which will be no units. So A3 will be a minus omega squared over 2 times 3 times omega equals minus omega cubed over 3 factorial. A5 will be minus omega squared over 4 times 5 times minus omega cubed over 3 factorial, or omega to the 5th over 5 factorial. And so it looks to me like then A sub n will be -1 to the n plus 1 because it's alternating. Omega to the n. Actually, no, because n is, you know what? Let's just do it like this. Let's just simply say that x of t is equal to omega t minus omega cubed t cubed over 3 factorial plus omega to the 5th t to the 5th over 5 factorial minus et cetera, et cetera. And that is sine of omega t. All right, any questions?
Yes, Professor.
Yeah.
could we assume that the solutions are of a different form and then get some weird different solutions?
What do you mean by that?
Like say X equals some other, not a power series?
Sure, we could assume that X is a Fourier series, and we didn't really cover that in here, but there are cases where people will have differential equations where the coefficients P and Q are periodic functions. And when P and Q are periodic functions, then it's more appropriate to write your solution as a Fourier series. And this is a major topic in solid state physics when you're studying electrons and periodic potential. It's a major topic in optics when you're dealing with photonic band gaps. So you're solving the wave equation in a medium where the index of refraction varies periodically. There are times when we're going to spend a couple of weeks learning about like Legendre polynomials and Bessel functions. There are times when people assume that the solution is a sum of Bessel functions, or they assume that the solution is a sum of Legendre polynomials. But we can't do that until we first outline what are the properties of Legendre polynomials. I've been introducing them here and there. Well, next week, we're going to actually solve the Legendre equation and study them systematically and see where the Legendre equation comes from. And then we could start breaking down solutions to problems into a series of Legendre polynomials. Any other questions?
Is the reason why we can represent these as periodic functions because the null space of the function, as in you can add like any component on the null space to the whatever equation you derive, and it still results in the same thing.
I don't know what you mean by the null space of a function. I know what the null space of an equation is.
Null space of the equation, sorry.
Well, technically, it turns out that the solutions to these periodic problems don't have to be periodic, but they can be written as the product of a very simple function multiplied by something else that has the same periodicity as the refractive index or as the potential energy that the electrons are feeling. And so I think of it as coming from the symmetry. It has to be that if we go from, say, over here at one atom to over here at another atom, the wave function has to be the same up to a phase shift. And whatever the phase shift is from here to here, it better be the same from here to there, and then from here to there, and here to there. The reason why the amplitude has to be the same is because the probability of an electron being on this atom had better be the same as the probability of an electron being on this atom, or this atom, or this atom. Likewise, with the light, we've got some mode where you've got regions where the light has very high energy density and low energy density. And these things are propagating, but the spacing between the peaks and troughs of the energy density had better be the same everywhere, and the phase shift will determine how it propagates. And I realize I'm going through that quickly, but we can talk about this more in office hours. What I want you to take away right now is that there are a whole lot of ways that we could write solutions to differential equations. I promised you at the beginning of the semester that what we would be doing is talking about different ways to represent functions by breaking them down into different kinds of pieces. And right now I'm building up the tools we need to solve the differential equations that define some of these key sets of functions. We introduced Legendre polynomials just kind of by fiat a few weeks ago. I just said, okay, here are these polynomials. They have these properties. You take their inner product and you get 0 if you multiply two different polynomials. And now I'm trying to build up the techniques that we would use to solve an equation whose solutions will turn out to be Legendre polynomials. And next week, we will actually solve that equation. Right now, we're solving simpler equations of that form. Next week, we'll actually solve that equation and show that that equation is part of the wave equation. So let's get back to actually building up the tools for this. I want to talk about the Hermite equation, because I should say at least a little bit of something about the Hermite equation at some point, and it illustrates something that shows up a lot in solving these kinds of equations. So let's go back to the Hermite equation, which was d squared psi dx squared minus 2x d psi dx plus 2 nu psi. Now this equation does not have a singularity, so we're not going to have to worry too much about things. And we're going to say that psi of x is the sum from n equals 0 to infinity of a sub n x to the n. And d squared psi dx squared must be what we got above. It must be this just replacing x with t. So I'm going to just use that. I'm going to take this thing that we just derived and use it rather than reinventing it from scratch. So that's going to be the sum from n equals 0 to infinity a sub n plus 2 times, let me make sure I've got it right, n plus 1, n plus 2. But 2x d psi dx, you may be thinking we have to do a shift, but just hear me out. Just watch what happens here. We're going to have 2x times the sum from n equals 0 to infinity of an n times x to the n minus 1. All right. Looks like we're going to have to do some sort of shift, redefine some other variable that's equal to n minus 1, except that we've got this x out here, which I can multiply in there. And I just get 2, or I'm going to write this whole thing in there. The sum from n equals 0 to infinity of 2n a sub n x to the n. And then, of course, 2 nu psi will just be the sum from n equals 0 to infinity of 2 nu a sub n x to the n. And if I put all this together, I get the sum from n equals 0 to infinity of n plus 1, n plus 2, a sub n minus 2 nu, sorry, a sub n plus 2 minus 2 nu a sub n, sorry, minus 2 n a sub n plus 2 nu a sub n, whole thing multiplied by x to the n. Any questions on how I got that? It all just comes from this equation. The minus 2x d psi dx is here, and then the plus 2 nu psi is there. All right, well, again, all of this has to add up to 0 if this differential equation is satisfied. That means that every single term in here had better be 0. So we've got n plus 1, n plus 2, a sub n plus 2 equals 2 times n minus nu yeah, 2 times n minus nu a sub n, or a sub n plus 2 is equal to 2 times n minus nu a sub n over n plus 1 times n plus 2. Any questions on how I got this? Well, here's one thing to note about this. This is not going to line up nicely with any function you've seen before. It's not going to line up exactly with any function we've seen before. But as n goes to infinity, meaning as we get really far out into the later terms of the power series, and we want to get out into the later terms of the power series, because as we get out to the later terms of the power series, that's going to tell us whether or not this thing converges. N minus a giant number minus a small number is almost the same giant number. And a giant number plus 1 and a giant number plus 2, almost the same thing. So this is going to be roughly 2 over n a sub n. All right? So if we say that a sub 0 is 1 and a sub 1 is 0, then, and that would just be one type of initial condition. If that's the case, then for even n, we get an even function that is roughly, you're going to say, well, this is not exactly correct. And you're right, it's not exactly correct. But we're going to get roughly 1 plus 2t squared over 1 plus, every time we go through, we're going to multiply by 2 up top. So we're going to get 4t to the 4th over 2 plus 8t to the 6th over 2 times 3, because here n equals 1, sorry, n equals 2. Blah. I should have followed my notes more exactly. N equals 2, n equals 4 times 2 times 4. Here we're going to have 2 times 4 times 6. All right. And then we're going to have 16t to the 8th over 2 times 4 times 6 times 8. Now what we've roughly got is 1 plus t squared plus t to the 4th over 1 times 2 plus t to the 6th over 1 times 2 times 3, because I'm just dividing everything in the bottom by some 2's. Here I've got 2 2's. Divide each of these by 2. Here I've got 3 2's. So I divide each of those by 3. Here I've got 4 2's. So I divide each of those by 2. So I've got, that was terrible handwriting. I'm going to get hospital privileges soon if my handwriting gets any worse. Okay, what does this look like to you? I've got t to higher powers and I've got a factorial on the bottom.
Cosine.
X of t squared.
Yeah, it looks to me like the exponent of t squared because I've got 1 plus t squared to the power 1 over 1 plus t squared to the power 2 over 2 factorial plus t squared over the power to the power 3 over 3 factorial plus t squared to the power 4 over 4 factorial. The reason it's not a cosine is because things aren't alternating. So it looks like e to the t squared. Why did I write t? I switched from t to x partway through. I apologize. Or e to the x squared if I were consistent. And at this point, we could say, all right, well, is e to the x squared a valid solution? Yes, but e to the x squared has a convergent series, i.e. the series does not blow up, all right? The series can have a huge value. If x equals 10, then x squared is 100, and e to the x squared is e to the 100, which is some ungodly huge number that probably exceeds the number of, it exceeds a whole bunch of really big numbers in astronomy. If I try to remember off the top of my sleep-deprived head exactly which astronomical number it exceeds, I'm going to get it wrong. E to the 100 is a huge number. But this converges to that number, which means if I keep adding more and more terms, my series will get closer to e to the 100, and it won't just go off to infinity. You could say, well, it goes to e to 100, that's huge. Sure, but it has a stopping point. It's a huge stopping point, but it's a stopping point, all right? That's a convergent series. A series could converge to a number that's ungodly huge, but it still converges. So e to the x squared has a convergent series, but in quantum mechanics, we don't want functions like that. We want a function that doesn't get ungodly huge. We want functions more like that, not like that just blows up, okay? And so in order to avoid a function that blows up to something ungodly huge very rapidly, we want something that we can integrate. What if nu is an integer? Because what I was giving you was just an approximate or asymptotic form of it. I was saying, all right, if we have many, many terms in this series, if our series goes out with, to some huge number of terms until eventually n is much bigger than nu, whatever nu is, we just go out even farther than that. Then I said that eventually our series starts to look like this. The earlier terms may not look exactly like that, but the later terms will converge to something that looks like e to the t squared. an plus 2 equals 2 times n minus nu times an. I'm going to rewrite this here. I'm going to copy, and then I'm going to paste if it will let me. Will it let me? Whatever. Cancel that, whatever. an plus 2 is equal to 2n minus nu an over n plus 1, n plus 2. And I'm harping on this not just because of the Hermite polynomials, but because there are a lot of types of equations like this where we want something to be an integer and then something cuts off. Say nu equals 8. Okay, so then A10 would be 2 times 8 minus 8 over 8 plus 1 times 8 plus 2. So we're going to look at the case n equals 8, n plus 2 equals 10. So A10 is 0. Then A12 will be 2 times, times A8. So A12 will be equal to 2 times 10 minus 8 times A10 over 10 plus 1 times 10 plus 2. But this is 0, so that'll be 0. And A14 will be 0, and A16 will be 0, etc. So if nu is an integer, you eventually reach a stopping point. Right? If n equals nu, then anything after nu, if nu was 7, well, A7 could be non-zero, but A9 would be 0, and A11 would be 0. This series would not go to 11, disappointing spinal tap, and A13 would be 0, and so forth. So if nu is an integer, then series stops after n equals nu. So the solution is a finite polynomial. The infinite series may be valid. The infinite series may be something a mathematician would look at e to the x squared and say, that's cool. A mathematician would look at e to the x squared and say, that is a well-defined function. We can take derivatives of it. It's continuous. What's the problem? A physicist would say, well, it's a function that blows up very rapidly as we go out to infinity. And a mathematician would say, so, and a physicist would say, well, we happen to know that that does not describe the harmonic oscillator. And a mathematician could say to you, well, does a polynomial actually describe the harmonic oscillator? And the physicist would say, well, the polynomial multiplied by a bunch of other things that you learn about in quantum mechanics does decay at infinity, because those other things decay at infinity. What you need to take away at this point is that when we solve equations like this, when we write down these series, sometimes the equation will have a parameter in there that, if it has an integer value, can cause the series to terminate and become a finite polynomial. And we do that either to make sure that the series converges or to make sure that the function has some other property that we care about. Next week with Legendre polynomials, we're going to do it to make sure that the function doesn't blow up. But sometimes, even if the function wouldn't blow up regardless, you still want a function that's a finite polynomial because it better describes the physics. And then if you pick the right value of this parameter, you can make the series behave nicely. Any questions? Somebody must have a question.
So if nu is an integer, the terms before the terminating term are all negative, right? Or they alternate.
They should alternate, yeah, because if nu is an integer, if n is less than nu, then n minus nu will be negative. So if, let's just do this. Let's say that A1 equals 0 and A0 equals 1 and nu equals 4, okay? So A2 will be 0 minus 4 times A0, which is 1, over 0 plus 1 times 0 plus 2, which would be negative 4 over 2, which would be negative 2. A4 would be equal to 2 minus 4 times negative 2 over 2 plus 1 times 2 plus 2, which is negative 2 times negative 2 over 3 times 4, which is 1/3. And then A6 would be 4 minus 4 times 1/3 over 4 plus 1 times 4 plus 2. And that is equal to 0, and the series stops. So yes, it would alternate. Any other questions? I want to talk about singular points now. We're not going to finish these today. We'll have to pick them up next Monday. But at a singular point, P and or Q blows up. In that case, it turns out that if we write our equation as d squared f by dz squared plus s over z df dz plus t over z squared d squared f, f, all of that equals 0. F of z can be written as z to the sigma times an analytic function, sum from n equals 0 to infinity of a sub n z to the n. And one thing you could ask is, wait, I'm multiplying by some power of z. Isn't that just another power series? Here's the big difference. A power series that has non-negative integer powers, its derivatives can't blow up. When the series is convergent, right? And the reason but this thing could cause the derivatives to blow up, because let's say that sigma equals 1/2, okay? So let's say we've got f of z equals z to the 1/2 times some analytic function of z, which I'm just going to call g of z. df dz would be 1/2 times z to the 1/2 minus 1 g of z plus z to the 1/2 dg dz, product rule. All right, you tell me, does this blow up?
If gz over square root of z blows up, which it might.
It might, yeah, this could blow up. I'm not guaranteeing you that it will blow up, but it could blow up. Now, if g of z was like z or sine of z, then sine of z over square root of z is not going to blow up when z equals 0. So there's no guarantee it will blow up, but it might blow up. okay? And so because it might blow up, and you could say, well, maybe it doesn't blow up, but then we could take the second derivative. We're going to get a 1 over z to the 3/2. And then we could take, and you could say, well, maybe, you know, our analytic function was z to the 4th. So, you know, z to the 4th over z to the 1.5, that won't blow up. Well, then we could take another derivative and we'll get, you know, z to the 4th over z to the 2.5. Still doesn't blow up. Another derivative, z to the 4th over z to the 3.5. Still doesn't blow up. But I take yet another derivative, z to the 4th over z to the 4.5. That blows up. So we can easily get something that eventually blows up. One of its derivatives blows up. And if one of its derivatives blows up, that's not a power series, okay? That is not a power series with just non-negative integers in it. So what we're doing is we're writing it as a product of something nicely behaved and something that could be singular. And there's no reason it has to be square root. What if I had z to the 10.1? Well, z to the 10.1 doesn't blow up. And its derivative, which is proportional to z to the 9.1, that doesn't blow up. And the second derivative, z to the 8.1, that doesn't blow up. But if we take enough derivatives, eventually we get z to the 0.1, still doesn't blow up. But one more derivative and I've got z to the minus 0.9, that could blow up. So all of these things eventually have discontinuities. You take enough derivatives and one of them blows up. And since Taylor series are all about derivatives that don't blow up, this can't fit into a Taylor series. So we take the singular part, the part that doesn't fit inside, that can't be described by a Taylor series, and we factor it out. And there is a theorem that we can do this as long as the equation can be written in this form, where S and T are non-singular. How do we figure out what sigma is? What is sigma? Besides, of course, the Greek equivalent to the letter S. And the answer is that we have to actually plug it into the Taylor series, and we have to plug it into the differential equation and see. All right, so if we take d squared f by dz squared, well, let's do this one step at a time. df by dz is going to be the sum from n equals 0 to infinity of sigma plus n, an z to the sigma plus n minus 1. And you say, why am I putting the sigma back in there? So that I don't have to use the product rule when taking derivatives. If I did, I would get something much messier that would eventually simplify to this. Then d squared f by dz squared would be the sum from n equals 0 to infinity of sigma plus n minus 1 times sigma plus n an z to the sigma plus n minus 2. And if I put everything together, remembering that I have to divide by z, when I multiply by s, I have to divide the derivative by z, and I have to divide f by z squared. I get that d squared f by dz squared plus s over z df dz plus t over z squared f is equal to this bloody god awful mess. Everything has an an. Everything has z to the sigma plus n minus 2. Okay? Because the second derivative has sigma plus n minus 2 from taking two derivatives. The first derivative, I only subtract 1 from taking the derivative, but then I divide by z. And the function, well, it should just be sigma plus n, except I divide by z squared, which subtracts off a 2. So I get sigma plus n minus 1, sigma plus n, plus s of z, sigma plus n, plus t of z. And all of this has to equal 0, which means each term equals 0. Last point. If n is greater than 1, then I could also rewrite this. I could factor out the singularity. I could write this as z to the sigma minus 2, potentially singular part, times the sum of an z to the n, sigma plus n minus 1, sigma plus n, plus s of z, sigma plus n, plus t of z. And all of this has to equal 0, which means that this whole thing has to equal 0. For z equals 0, the n greater than or equal to 1 terms are 0. For n equals 0, we're going to get sigma minus 1 times sigma plus s of 0 times sigma plus t of 0 equals 0. And this is a quadratic equation. Similar to what we got with the Euler equation. And we will pick up with this on Monday. Besides the midterm this Friday, remember that for Monday, there'll be a practice assignment that will show you how the Legendre equation is related to the wave equation. So Monday, we will do a little bit more with these singular functions. Then we'll go to the Legendre equation and spend next week on the Legendre equation. And then we'll do the Bessel equation the following week. Have a good day.
Thank you, Dr. Small.
You're welcome.
Just a couple questions about homework, Dr. Small.
Sure.
So this Wednesday is a holiday, so we
There's
won't
nothing
have,
due this Wednesday.
but it will be due the following Wednesday. So does that mean there's 2 problem sets due that day?
No, there's just one problem set due next Wednesday. I wrote that on the syllabus. There's only
Okay,
problem set due next Wednesday.
got it. Okay, thanks, Dr. Small.
You're welcome.
Hey, Dr. Small,
Yeah.
is the Hermite from the Hermite equation the same as the Hermite from Hermitian, like a Hermitian matrix?
I believe so. I'm not 100% on that, but I'm pretty sure.
That's cool. All right. Thank you, Professor.
Mhm.